Good morning, Professor.
Good
afternoon, Professor.
Good afternoon, Caroline. Good afternoon, Amy. Good afternoon. That's awesome. Oh, and of course, I just lost my board as you said that. Good afternoon, Alicia. Good afternoon, Amanda. Good afternoon, Caitlin. Good afternoon, Kevin. Good afternoon, Jamalette. Good afternoon, Sophia. Oh, and I'm seeing some. Oh, wow. There's like they're both okay. And she's. Oh, good afternoon, David K. Good afternoon, Sophia. I said Jamalette. Good afternoon, Felicia. Hi, Christina. Okay, wait. Oh, and someone else just, we're going to get straight. All right, this is it. I'm going to try to be quick. And I lost my board. I'm very much hoping to see you all next semester, one way or another, in 2D or 3D in 204. Very quickly now, just fixing the board. Hopefully you. So again, we still, well, we have one class today to bring the material to close. Hopefully you all saw the practice exam. I'm going to try to say a lot of things about the practice exam today. I mean, mostly that's all I'm going to talk about today. Certainly any questions you have, today's the time to ask, although of course you can also ask by text or by email afterwards. And please put them in the chat. Hold on, just again, I think it made clear, like the actual exam will be posted like Wednesday night, and then it'll be due back next Monday. I think we said that. Again, you can work with other people, blah, 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 but your final thing has to be yours, all that. But any questions? In fact, I'm going to, one last time, I think the most important thing, you have my, I'm going to just put in here, any questions from here until the end, that, and someone else, and also that, hold on, I know someone's here in the waiting room, we'll get them in 1 second. Okay, and someone's in the waiting room. Okay, and good afternoon. All right, so again, any, you know, your final, there goes the board again, but okay, so it'll be, the final thing will be posted Wednesday, it'll be due back Monday, and we're done. You'll get, again, I'm telling you right now, I will put more weight on, somehow or other, I will put more weight on the, whichever of the two exams you ended up doing better on, especially for those of you who've had to wait super long time. There's more, you got a few points for your patience for that. And with all of you, if you do better, whichever exam you do better on will be weighted slightly more in your average, then all the homeworks and all that will help your average, blah, blah, blah. If you have concerns, you can, I'm just rushing because I'd like to just finish this material for you. And because my board keeps disappearing, hold on. Hold on. Okay. So here's what I want to do. I'm assuming you have the practice exam in your possession, hopefully maybe even open, you know, in front of you. I'm not saying it's easy. I'm not even saying that I'm not saying the practice exam is easy. I'm not even saying that the practice exam is short. I'm saying a couple of things. One, hopefully most of it is not a surprise, even if it looks hard. It's hopefully what, you know, you were kind of expecting at this point, or what I told you to expect. I'm not saying I won't post some hints or solutions or answers. I might still do that before Wednesday. I might even do it if I can while you're working on it. Like I might post things to be more helpful about it. So I'm not saying this is the end of the helpful road or anything like that. Also, also, I know the practice exam is kind of long, and I don't really want your final exam to be long. So there may be places in your, or as long, so there may be places in your final exam where I give you choices or I cut certain things out. That may well happen. Definitely your final exam won't contain anything you don't see in that practice exam. It's just that maybe some things I'll take out. So as long as you fully, know this practice exam, then you're set. What I'm going to do right now, just things keep getting interrupted. What I'm going to do right now, besides let more people in, is I first just want to, as quickly as I can, I want to give you two last equations where you're sort of asked to do a plug and chug with these equations at the end of the practice exam. Like if you turn to the I think it's the very last page of the practice exam, you'll see one question about a spring and then one question about gravity, about universal gravitational force. Those are the only two questions that are sort of new or like not about material that we've been doing for weeks. So I want to quickly tell you how to do them right now. Like if you're paying attention right now, it shouldn't be a big issue. I just want you to have that knowledge planted in your brain before you go on to Physics 204, okay? So I'm going to turn the page. So I'm going to do those first. In other words, again, if anybody is listening right now, what I'm about to address, I think lands on the last page of the whole practice exam. I'm going to get that sort of out of the way. And then I can be more general about the whole thing and certainly, again, answer questions if you put them in the chat. All right. So I hope everybody's with me. I first want to address something about that spring question at the end. And honestly, I'm looking at my board. Anyway, on the last page, on the last page, the thing goes down a ramp and then it hits a spring and it asks some question about the spring. Here's the deal with that. Okay. So you'll notice there's a couple of questions on the very last page where it tells you something about positions. Like it says the mass fell from a certain height and asks you the speed at the end of its fall, like it falls down a curved ramp or something. It gives you the height of the ramp and it asks you how fast it's going at the end of the ramp. Then the mass like hits a spring and it asks you something about how far the spring gets compressed. Questions that relate speed to position, okay? And again, this is entirely about the last page and entirely about Physics 204. And again, these are ultimately a couple of plug and chugs I just want to set you up for right now. But in physics, any situation where you're told the speed if you're told the speed at a certain position and you're being asked to know the speed at another position, or vice versa, you're told the speed at a certain position and you're asked at what position will a certain speed be attained. If ever you're given like a one-to-one correspondence between speed and position, in other words, if you're given questions that don't seem to have anything to do with time, questions that just relate speed to position, but to instantaneous speed or instantaneous velocity to position, but don't seem to have to do with time. These are questions that have to do with questions that relate speed to position ultimately have to do with something called the conservation of energy. here's how conservation of energy works. Recall that one of the last things we said last class, and this all has to do with the very last lab you ever did in class as well. The very last thing we said in the last class is that if you exert a force through a little displacement, if you exert a force F through a little displacement, delta X, you do something which we call work, okay? 1 joule of work, in fact, 1 joule of work is defined to be is equal to 1 Newton of force times 1 meter of displacement. Now, why do we care? Well, so when you exert force through space, if you don't just exert a force at one moment or one point in space, if you exert a force through space, we say that you're doing work on an object. Why do we care? Why do we do this? Because notice, what we've been saying for weeks and weeks and weeks is that the net force you do on an object accelerates an object, right? Net force equals ma, or sum of all the forces equals mass times acceleration. So if you, and we had an equation from early in the semester, acceleration is change in velocity per time. But remember, we said early in the semester, if you ever have a situation where you know the acceleration and you know things about the velocity, but you don't know anything about the time and you don't care at all about the time, we said at the beginning of the semester, this is just an equation from the first exam. I'm just reminding you, we had an equation that we just got from algebra that said acceleration equals v squared minus v naught squared all over 2x. So if we substitute that in, if we plug that in and we say, and we multiply both sides. Let's say, in other words, if we want to calculate the work that a bunch of forces do on an object, the net work that a bunch of forces do pushing an object through a space or pulling an object through a space, I would multiply force by displacement to get work. So I'll multiply both sides of the equation by displacement. And I would get so I'll substitute in. Okay, so all I'm doing is I'm saying work is force times displacement. I'm multiplying force times displacement to get work. Therefore, I'm multiplying the other side, ma times displacement. And I'm substituting in for a, v squared minus v naught squared over 2 delta x. Delta just means a small amount of x, a small displacement. So the delta x's cancel. And if you don't like delta x, if you just want to call it x, that's fine too. It doesn't make any difference for this. They cancel. And what we find, well, I could turn the page back if you want. It's just a little algebra that says the net work that we do on an object is that, okay, this is just algebra. Again, I'm just combining together pieces of knowledge that we have. That net work is force times displacement. For net force is ma, mass times acceleration, and I'm just plugging in an equation for acceleration and rewriting. So it says all I did was just algebra right now, but what the algebra shows is that if I do net work on an object, if I push an object, if I exert a force on an object through a displacement, I change the amount of 1/2 mv squared it has. What do I mean by that? I mean, remember any other equation you had from the beginning of the year, such as displacement equals final position minus initial position, x minus x naught, or you had like average velocity equals x minus x naught all over t. Average velocity equals, or you had average acceleration equals v minus v naught all over t. And every time we had one of those equations, when we would see something minus something naught, we always said, oh, that's the change in that variable. That's the difference in the value of that variable. For example, if we see x minus x naught, we say, oh, that's final position minus initial position. That's the change in position from before to now. That's what we call the displacement of an object. Or if you see v minus v naught, it's final velocity minus initial velocity. So that's the change in velocity from before until now, right? Whenever we see a variable minus the same variable sub naught, we're saying final value of that variable minus initial value of that variable, the difference in the value of that variable. So apparently, right? So apparently here, when you do net work on an object, you apparently change the value of its 1/2 mv squared. You change it from 1/2 mv squared old, like 1/2 mv naught squared, 1/2 the mass times the initial speed squared, to the new value of 1/2 mv squared, 1/2 mv squared minus 1/2 mv naught squared. Now, I'm not saying that we ever cared about 1/2 times m times v squared before. I'm saying this is new. And this is as far as we go with it. But I'm saying it's a discovery that we're saying, oh, if you push an object through a distance, if you do work on an object, what you do a number of joules of work on an object, a number of newtons times meters. Oh, someone's here. Hold on a second. What you do is you change something about that object. You don't change it. Like if you do 5 joules of work on an object, you don't change its velocity by 5 meters per second. You don't change its mass by 5 meters per second. But evidently, if you were to take that object, take its mass, like plug it into like your head, divide it by 2, so take half of its mass in kilograms, put it in your head, and then take its speed, or let me start again. Let's say you take the object, take its speed and square it. So and put that number in your head and multiply that number by 1/2 of its mass. So you cook these numbers together and put them in your head, or you write them down on a piece of paper and track it, like 1/2 of its mass times the square of its speed. If you then push the object through a displacement, you'll notice that when you're done at the end, if you were to calculate and write down the square of its speed times 1/2 of its mass, the difference in the two numbers would be exactly the number of joules of work you did on the object. That's just what the algebra says. Now, I'm not saying that I ever cared about 1/2 of the mass of an object times the square of its speed before, but this equation now, for the first time in my life, tells me to start caring about that. It says that if you start tracking the 1/2 the mass times the square of speed of an object, you'll notice that it changes, that product of numbers, that lump product of that lump multiplication of measurements, that total amount will change by exactly the number of joules of work you do on an object whenever you do joules of work on an object. So we start tracking this quantity. From now on, instead of calling it the like half mass times square speed of an object, from now on, any object at any moment, at any speed, you take its mass, you multiply by the square of its speed. Think about the units. In other words, you take kilograms, you multiply it by meters squared divided by seconds squared, right? You'll get kilograms times meters squared. You'll get kilograms times meters per second squared times meters. And a kilogram times a meter per second squared, a mass times an acceleration, is a Newton. Right? And and meters, displacement is measured in meters. A Newton times a meter is a joule. So I'm saying from now on, the amount of work you do on an object measured in joules is the amount by which you change its kinetic energy measured in joules. Okay, kinetic energy of an object is 1/2 its mass times its square of its speed. It's measured in joules. If an object has 3 joules and you do 4 joules of positive work on it, you will give it 4 more joules of kinetic energy. It will speed up, not by 4 meters per second of speed, but it'll speed up by having 4 more joules of 1/2 mv squared. From now on, the work that we do on an object is the change in kinetic energy. And remember, work is force times displacement. So the bottom line of the work, this is called the work kinetic energy theorem. Work is the transfer of energy. If I do positive work on you, I give you energy. Where does the energy come from? It comes from me. If I do 5 joules of work on you, you gain 5 joules of kinetic energy. I lose 5 joules of kinetic energy. Work is the transfer of energy. And what is energy? What is energy? And then we're just almost done with this. Oddly, what energy is 1/2 mv squared. What work is force times displacement. What energy is 1/2 mv squared. What does that mean in English? It means this. Work is the act that you perform on another object to give it energy. If you do positive work, you give it energy. If you do negative work, you take energy away. Work is the act you do on another object to give it energy. What's energy? Energy is the ability to do work. Sounds like a circle. Sounds like a circle, and it is kind of a circle. It's literally like saying a transaction. It's like economics. Transaction is the act of passing money from one person to another. What is money? Money is the ability to perform a transaction, right? That's it. Like, why do I ever want money? Because the more money I have, the more I can spend. When I spend money, I get other things that have a value that's equal to the money. When I give you money, I have less, you have more. What do you care that you have more now? Because now you could give that money to someone else in exchange for some other good. Same thing with energy. The reason I have energy, if I have kinetic energy, it means I'm really big and I'm moving really fast. Why do I care? Because I can smash into something else and get it to start moving really fast. If I smash into something else and get it to move fast, I'm going to move slower. It's literally like that. Energy is just a commodity you have that enables you to affect the amount of energy that other objects have. And we just pass it around. The more you have, the faster you're going. The less you have, the less slow you're going. The more you have, the more the ability you have to transfer it to other things and get them going faster or slower. Okay, so work is the transfer of energy. Energy is the ability to do work. It really is that straightforward. And as far as the exam, and then I'm going to move on. Okay, as far as the exam, right? So remember, we said work. I'm just looking at the time. Okay, 12. So work, we said, is force times displacement. Let's take the example again. This is all about the last page of the exam. And also, let me just say, I'm saying a lot just so we can finish it. And I'm going to go back and answer questions about all the other pages and stuff like that. But I'm saying a lot so we could tie this whole thing together. And I will stop in a few minutes with this. But everything I'm saying now is this last topic. It's only so that you can get a couple of those last questions fully correct and understand them. Even if you get the whole rest of the exam right and you don't nail those questions, that's not a big deal either. I mean, don't lose too much sleep over it. So don't, even if I'm going a little bit fast right now, don't let it get to your head too much. I'm just trying to tie up these loose ends before the semester ends. So the work done by gravity is the force of gravity times the displacement through which gravity acts. The force of gravity in the context of this exam and all that is mg, like weight, right, is mg. Mg is a force that pulls down. So it pulls things down from one height to another. Gravity fully points vertically straight down. So the only displacement that it cares about, the displacement over which gravity acts, is vertical displacement, height. Like the difference between one vertical position and another. So the work done by gravity is literally force of gravity mg times the displacement over gravity x, and h. That's it. The work done by gravity is mgh. So this is much like your lab 6 or whatever. Like if you have this block of mass m and it slides down a smooth ramp of height h, it says this in the exam, right? I'm saying, and it starts from rest, and we're asking in the exam, what's the final speed that it has at the bottom of the whole thing? How we do it is we just say, okay, work equals change in kinetic energy. The work done by gravity is mgh. That will change the kinetic energy from some initial value 1F mv naught squared to some final value 1F mv squared. But the block started from rest. The initial value is 0. So the m's cancel out, and the final speed at the bottom of the ramp will just be square root of 2gh, if you're following me. I know I'm going a little bit fast, a little bit, but that's it. In other words, I don't care that the ramp is curved. It doesn't matter. As long as I know that the ramp is h high, then the total amount of work that gravity does, exerting a force of mg through a vertical displacement of h, the total work is mgh. The work that gravity is doing on the block gives it a certain number of joules of kinetic energy. It raises its joules of kinetic energy from 1F mv naught squared to 1F mv squared, but mv naught squared was 0. So if I'm solving for the final V, I just divide both sides by 2 and square root both sides, and that's the answer to that. We're okay. Again, we're going to take a pause in a second, but we're almost done. Then what do you do with springs? Springs, same thing. Work equals force times displacement, we said, right? And by a spring, oh, cool. Thank you. Awesome. I'm actually relieved of all days to say that. Good. Okay, I'm glad. And we're almost okay, good. Thank you. The work done by a spring, I mean, the force exerted by a spring is negative kx, we said last week, right? The whole point of a spring is the farther out you hold it, the stronger its restoring force is. Like, that's what it means to be springy, is that springs exert a greater and greater force the farther and farther you hold them from equilibrium. So the thing with a spring is, the farther and farther out you're holding a mass from its equilibrium position on a spring, like imagine one end of the spring is fixed to a wall and you're holding out the other edge. If you just held the edge at equilibrium, if you weren't pulling out the spring at all, then the force would be 0. If you pull it out to 1 meter, then it's 1 meter times K, whatever the stiffness, the constant of proportionality is of the spring. If you pull the spring out to 2 meters, then it's 2 times K. You pull it out to 100 meters, then it's 100 times K, negative 100 times K, right? Like, the K is a constant, but the farther out you're holding the spring, the stronger the force. Right. So what is the work done? Like, if you want to know the work done by the spring on the mass when the mass is just only at 0, it would be 0. If you wanted to know the work done on the mass when the mass was all the way at x equals 100, well, then the force is K times 100 and the displacement would be 100. So it would be K times 100 times 100. Right. Like, the X comes in twice. The force is dependent on X and the work is dependent on X. So what's the total amount of work for the whole thing? Well, 0 would be too small, and 100 times X would be too big, because that 100 is only what's true when the mass is all the way out at 100. So that's too big for all the other places. And 0 is too small. It's only true when the mass is all the way at 0. So that's too small for all the other places. So on average, work equals 1/2 of F times X, which equals, oh, sorry, I mean 1/2 KX times X, right? So this is the average force. And this is the displacement. Because work equals force times displacement. So on average, the work done by a spring, on average, the work done by a spring is this. Work equals 1/2 KX squared. KX squared, because the force is KX and work is force times displacement. So it's KX times X. We would just say KX squared, but we're saying 1/2 because if we said KX squared, we'd be all the way at the final X position. I'm looking. Wait, great question in the direct chat. So this is the answer. And luckily we're just about done with this. I mean, I don't have to say much more about this. That's the good news. But there's a great question in the direct chat. Why is W work? Should it be kinetic energy or joules? Here, this is in the direct chat. Sorry, let me say that slower. The question in the direct chat is, why is W stand for work? Shouldn't it be kinetic energy or joules? Great question. Here's what I'm trying to say. Work is measured in joules. Joules are the units. And yes, work is measured in joules. That's true. Kinetic energy is also measured in joules. And I'm saying that work and kinetic energy are actually very, very related. Very related. What I'm ultimately trying to say here, to answer this direct chat question, but also to bring this all together and then move on, I'm saying ultimately, work done on a system, work done equals change in kinetic energy, or equals transfer of kinetic energy. The person who's asking in direct chat is really asking a very important question. I am saying that work and kinetic energy are very, very similar, very related. They are both measured in joules. So all the work I'm doing right now with these calculations is I am talking about joules. Absolutely. The subtle difference between work, the subtle differences, I'm not saying that work is kinetic energy. I'm saying that work is like a verb. Work is an act that you do. Kinetic energy is a noun. It's a thing that you have. So when I do work on you, I give some of my kinetic energy over to you. Work is the transfer of kinetic energy. If I do 5 joules of work on you, that means I give 5 joules of my energy over to you, which means literally, so this is why I use the words transfer or change. If I do 5 joules of work on you, it doesn't mean you have 5 joules of kinetic energy. I mean, it might, but it doesn't necessarily mean that. If I do 5 joules of work on you, it means that you now have 5 more than you had before. In other words, force times displacement equals change in kinetic energy from whatever you had before to whatever you have now. Change for difference in old kinetic energy, 1/2 mv naught squared, to whatever you have now, 1/2 mv squared. It's a change. So again, it's like money or transactions, like money and cost in a way are both measured in dollars, but they're not the same thing. Like something costs a certain amount of money, but I have a certain amount of money. They're both measured in dollars. If the soda costs $5, that means I have to give up $5 to you. So if you're selling me the soda, so now I have $5 less and you have $5 more. So work is when you give, you do positive work, you give over joules of energy. Work is the act, energy is the commodity. I don't know if that helps, or maybe the person in the direct chat, that was a great question. I don't know, maybe you can tell me if I answered it or not, but how I'm going to relate it. Okay, that's fair, that's honest. Okay, cool. And this may help more. This is what I'm ultimately saying, and then this is all I need to say about this exam or this page. And again, this is just a matter of you trying to get every question perfect if you can, but what I'm ultimately saying about the spring, so for a spring, and honestly, and yes, I'm trying to reduce these to plug and chugs. I don't need a ton of, I know I'm just showing you this right now, all of you people. So you just sort of want to get these answers right on the exam, and you don't have to make a big deal. But for spring, I'm saying the work done on a spring would equal the change in kinetic energy of that spring. Right. So if right. So if something slammed into a spring with a certain amount of energy and it was brought to rest, on the exam, where something hits the spring, it starts with a certain amount of speed, a certain amount of energy, and it asks, how far does the spring compress X? I'm basically saying, do this. I'm saying the mass comes in with a certain amount of energy, 1F mv squared. It's going to do work on that spring, 1F kx squared. So all the amount of energy it gives up from all the amount of energy it gives up in slamming into the spring goes into the spring and compresses it a certain amount of distance X. So the energy that the mass loses from speed does work on the spring. And 1F kx squared is the work done on a spring, 1F mv squared is the energy changed by the mass, and that's it. Okay, again, just leave, I mean, you can ask more. I'm not saying don't ask more questions, but this is a minor part of the exam. I just wanted you to see this before we're going to Physics 204. Look, and maybe I'll even think about whether I'll leave it in the exam or not. I just want everybody to know everything that's there. I'm going to pause there for a second because we still have a half hour. So that's it for that. I'm going to pause here for a second to get my thoughts together. Yeah, okay. Let me pause there. I'm not sure. The person who asked the question in the direct chat was a very good question. They honestly said in the direct chat that helped, which I think was an honest way of saying it helped, but I might not have fully satisfied them, which is fair. We'll let it sink in for a minute. Again, it's not the biggest part of the exam or anything. What I want to do now with a half hour left is just pause. And again, by the way, I'm not saying that I won't post some more solutions and stuff. I will try. I just can't promise exactly what I'm going to post and whatnot. But what I want to say now is I think everything else for the most part, all the other pages, all the pages leading up to that, they're not easy, but they're things that we've been discussing for weeks and that you did in lab 5 and all of that. What I want to pause now and say is, with a half hour left, great question. Okay, hold on a second. Okay. Great question. Okay. Hold on. Let me just write the answer. I'll read the question out loud to everybody. No, I'm glad you guys are really paying attention. Hold on. Okay, let me just clarify. So person in direct chat said, they're admitting they're confused about what I mean by K for the spring problem. And they asked, is K the displacement, the height? Fair question. The answer is no. Height in that problem was H. Okay, height was H. What K means, and this goes to notes from last class, you can look them up in Google Classroom or the video or whatever. In the last class or last week, we said that for a spring, K stands for how stiff or strong the spring is. It's the constant of proportionality between force and displacement. A spring exerts a force, like if you put a mass on the end of a spring, and you pull out the mass, the spring tries to pull the mass back in. The farther out you pull the mass, the farther out you hold the mass on the end of the spring, the stronger the spring forces the mass to come back in. Or if you push the mass all the way in past equilibrium, the spring tries to pull it out. This is what elasticity means. Elasticity is defined by this thing called Hooke's law. Elasticity means that the force exerted by something elastic is directly proportional to the displacement that you subject the elastic material to. So the more you try to hold elastic material apart, the stronger the force it exerts. So if you were to make a graph, and this is what we did, you could, again, I'm not trying to, but you can look back to the notes from Wednesday. If you were to make a graph of displacement of a mass on a spring, put that on the horizontal axis and put force on the vertical axis, you would find a straight line graph. You would find that if you double the displacement that you're asking the spring to undergo, you would double the restoring force that the spring would exert. So force is directly proportional to displacement on a spring, but the constant of proportionality, the constant slope of that straight line is called K. K is how many newtons of force you get per each meter of displacement that you try to subject the spring to. So the force exerted by, so K is the stiffness, the strength of a spring. If the K of a spring is like 200 newtons per meter, that means for every meter that you try to pull it out, it exerts 200 newtons of force. If it's 500 newtons per meter, that means for every meter you pull out the spring, it exerts 500 newtons force. So a spring of K equals 500 newtons per meter is a much stronger, stiffer spring than a spring of K 200. So K is the stiffness of the spring. I'm ultimately trying to say now, see, okay, again, it's a good question. I don't know if I'm really, you may have to stop and think about all these things, but what I'm ultimately trying to set up, partly for next semester, is that from now on, when you exert, like most of this exam, all of this exam is about forces, right? The whole exam is about forces. Most of the problems, most of the pages are about exerting forces at one point in space and one point in time. The huge bulk of this whole exam is about free body diagrams, looking at one object at one point in space, at one point in time, asking all the forces on it, and saying whatever those forces are, you add them all up, you're going to know the acceleration of the object at one point in space, one point in time. Right at the end of the exam, we just introduced this idea for a little bit of the exam, this idea of what if you push objects through space? Not if you just look at them at one point in space, but if you push them through space, if you exert a force through displacement, then that becomes called work. So force is measured in newtons. I'm saying this to everybody now. I'm still hopefully helping with this question, but I'm saying this to everybody. When you exert a force, you exert something measured in something called newtons. If you exert a force through this space, if you push a cup, not just push it, but push it through across a desk, if you exert a force of 5 newtons for 3 meters of displacement, then you do something that's called 15 joules of work. Force measured in newtons times displacement measured in meters is called joules of work. Why do we care? Why do I care? Why am I throwing this into the last? Because when you do work on an object, when you don't just push it, but you push it through displacement, you give it something called energy. Energy is also measured in joules. Energy is 1F mv squared. Energy is how big you are and how fast you're going. It's like a certain combination of those parameters. How big you are and how fast you're going. It turns out if I push something for 3 Newton with 3 newtons of force for 5 meters of displacement, I'll do 15 joules of work on it. Who cares? What's the impact of that? The impact is I will give it 15 joules of kinetic energy. It'll be going 15 joules worth faster than it was before. Does that literally mean 15 meters per second? No, a joule is 1/2 of its mass measured in kilograms times its speed squared. But if you do these equations, these calculations, you could find out how much faster it's going. So ultimately, and then I am going to move on. I'm ultimately saying for that last page of the exam, like mgh equals 1F mv squared minus mv naught squared. As the thing falls down the ramp, gravity does work on the mass. It gives it energy. It brings it up to a certain speed by the bottom of the ramp. Then at the bottom of the ramp, now the thing is going at a certain speed. It slams into the spring and it does 1F kx squared work on the spring. So you can go all the way from how high, like by knowing how high the original mass was, you can go from that information all the way to how far the spring gets compressed by going through these steps, because when you do work, you transfer energy, and it's just like spending money. The point is energy can come in different forms. It can come through come through the work done by gravity. It can come through the work done by a spring. So just like I could take $5 and buy a Coke from you, and then you could take that Coke and sell it to somebody else for €6 or something like that, right? And so we went through these transactions, and at the end of the day, you have a certain amount of money that's different from when you started because we went through transactions. Same thing here, like an object starts at the top of a ramp, it doesn't have any energy at all, but gravity does work on it. So it gives it energy, now it has all this speed, now it has all this energy, and it gives it to a spring. So it does work on the spring, and the spring ends up getting compressed a certain amount. We now think of energy as a commodity that can be transferred from one object to another. And with these equations, that's how you can get from the h, that is the height of the whole thing, all the way down to the x, which is the compression of the spring. K stands for how stiff the spring is. It's a number that's just given in the problem. You're never solving for it. You're just leaving it as a letter K. Or you're told the number at some point, you don't have to solve for it. It just means how stiff the spring is. I'm going to leave it at, I think that's a great question. I'm going to sort of hope I sort of answered. I'm going to leave it at that for the moment. Oh, okay. And I see one other question in the direct chat. I see another question in the direct chat that is actually the other thing I was going to address. I just hadn't decided whether I was going to address it in the last 5 minutes or now. So I'm going to address it now. The other I'm going to say this. So this is one more completely separate equation for the semester. I'm going to say this now. It's total plug and chug. Okay. I'm just going to say it. If you get it, you can plug numbers into the final question on the final exam and get it right. It's not meant to be overthought. It's just a plug and chug thing. And you may have heard it in high school or whatever. I'm going to say now, to summarize everything in a way, we've gone through this whole semester of mechanics. What I've been trying to claim all along, whether it's sunken or not, is that each next topic, each next equation we've done is yet another extension of this larger idea of Galileo's principle of relativity. Everything we've done in one way or another is about how the laws of physics are the same at all velocities, in all frames of reference, in all coordinate systems. The laws of physics are the same on Earth as they are in Jupiter, as they are on the sun, et cetera, et cetera. So the one thing that's been happening all semester is we have all of these rules and everything, but we have this one exception all the time. That seems like things are always being pulled towards the center of Earth. It seems like the one force that's the exception to everything is that somehow Earth has this magical power to pull on everything towards the center of it with this amount, mg, this amount that we call weight. And I'm going to say now, it turns out, the last thing I want to say for the semester is, it turns out, if you're wondering ever, which people were for centuries and centuries and centuries, why does everything get pulled toward Earth all the time? Like, what makes Earth special that it's pulling everything towards the center of it all the time with this force mg? The answer is it turns out the reason things are getting pulled towards the center of Earth all the time is not because Earth is special. It's not that the laws of physics are different on Earth from where they are anywhere else or anything like that. It's that actually, everything is being pulled toward everything in the world. In the universe. This is the last thing. Okay, everything is being pulled toward everything, it turns out. You may have heard this in high school. If you have any two masses in the world, M1 and M2, any two masses, Earth and Coke can, Earth and brick, sun and Earth, Earth and moon, moon and space rock, any 2 points of mass in the world, if they are separated by a distance r, or d, you could call it, then it turns out there is a force of gravity being exerted by one mass on the other mass, which is directly proportional to the size of one, directly proportional to the size of the other, inversely proportional to the square of the distance between them. You don't have to memorize this. Like, it'd be, I mean, you can memorize it, or you may have heard this a million times. But I am saying you don't have to memorize any of these numbers or any of these. I'm just saying, if you have any two masses, such as the ones being given in the problem here at the end of the final exam, like if you have the mass of a block on a ramp, and you have the mass of Earth, or you have the mass of Earth and you have the mass of Jupiter, those two masses are automatically being pulled on each other. They're automatically exerting gravitational forces on each other, a gravitational force that's directly proportional to the mass of each one. In other words, it's mass 1 times mass 2 divided by the square of the distance between them. Why the square, why divided, we'll get into next semester. But if you just take the two masses and multiply by each other and divide by the square of the speed between them, and then take that whole thing and multiply it by this universal constant called capital G, which is a tiny, tiny number measured in Newton's meter squared divided by kilogram squared. You multiply the whole package by this tiny number. I mean, it's a crazy number, but it's tiny, 6.67 times 10 to the negative 11th. And again, you don't have to memorize it or anything, but if you take that number and multiply it by your mass times your other mass, then you'll have kilograms squared in the top will cancel out with the kilogram squared in the bottom of this crazy number. You'll have meter squared in the bottom. That'll cancel out with meter squared in the top of this crazy number, and you'll be left with newtons in the end of the day. If you multiply the mass of any one object times the mass of another object and divide by the square of the distance between them and multiply the whole thing by capital G, this number, you'll get the force of gravity that any one object exerts on any other object in the universe. In other words, I'm saying Earth is not the only thing exerting gravity on objects. Jupiter is exerting gravity on each one of its moons. Each one of its moons is exerting gravity on Saturn. Saturn is exerting gravity on us, etc. Everything is exerting gravity on everything else. But how much gravity anything exerts depends on how big it is and how far away it is. The closer two things are, the more they pull. The force is inversely proportional to the square of distance. And the bigger they are, the bigger they pull. The force is directly proportional to mass. Now that's it as far as like these new details. And again, if some of you have probably been craving like a bunch of details like this all semester, so now you have some concrete details, you can rock the last page if you want. If all of that just went too fast, if it was too overwhelming, don't over worry about it. It's just all about the last page. With 12 minutes now, that was answering the question that was in the direct chat about that one other part of the last page. So that's it right there. We have 12 minutes. I'm going to stop for a second. In fact, I'm going to walk away for a second. I want you to ask me questions about anything else on any of the other pages. I may not be able to give a full extensive explanation right now, and I may post more things, but I'm going to walk away for a second and let you think. I want you to ask me any questions about any of the other pages on the final exam to clarify directions or to give you a hint as to how to start something or whatever. But I'll be right. You think for a second. I'm just going to use the restroom for 1 second. I'll be right back. Okay. So any questions at all? I'm going to pull it up while we're. But if nothing else, I would suggest that you guys flip through it right now. I'm going to say this too. I really prefer, I think it'd be better if you guys ask me questions and if I just start babbling, but I'm also going to tell you this because I know that what I just did went a little fast or was probably a little like out of nowhere to some of you. I'm also going to say this. Wait, let me just switch the view. Hold on. Let me just make sure. Like, are you still with, like, raise your hand if you're still like hearing me right now. Cool. Thank you, Amy. Thank you. Okay. Thank you, Jamila. Thank you. Okay. Awesome. All right. So here's also what I'm going to do, because again, I'm despite what it may look like, I want this to go as well for you as possible. So I think I'm going to say this also. With 8 minutes left, I'd like to answer questions if at all possible, but I'm going to say this, and I'm going to tell the other section as well. Of course, I post these videos and all that. I'm going to say right now, in the other class, in the class that meets, at 3:05 today, I'm not going to do it all what I just did with you. With them, I will literally walk through as much of the exam as I can. Okay, like whether they ask questions or not, I will walk through, or I will turn the pages and look at the highlights, even of the stuff that I think is old. I'll try to sort of do solutions to as much as I can of the regular part of the exam. in the other section. And I'll post that. So please be aware if you're hearing me right now, like, in other words, you'll have two separate videos to help you do this exam. The other class, I'll just like walk through the main sort of older material in the exam, and I won't discuss these new equations. I'll tell them the same thing, that if they want to see these new equations to nail things to the last page, they'll watch your video. And if you want to see me actually like walk through a little bit more patiently the bulk of it, watch the other video. Does that, and wait, thank you, Felicia. Okay, I'll take that as thank you. And thank you, Felicia. And Savannah, your hand is up. I don't know if it was just up from, thank you, Amy. Thank you. But Savannah, is your hand up just up from before, or is that a question? If there's a question,
No,
please.
it was just up from before.
Okay. But is that all right? So does everybody, in case we went out in 7 minutes, just please know I will do a walkthrough a playthrough, so to speak, of Pokemon Scarlet. No, I will like walk through as best I can in the other video, but I needed to get these two equations out somewhere. So, okay. So now, but we still have like 7 minutes. I mean, I can make a choice as to what I think is the most, well, I'll start walking. Please interrupt me. Like, I'm sure there's a part that you'd rather see than that wouldn't occur to me, but I'll say this, like, yeah, I'll just like walk through it a little bit. Like, and by the way, even to me, it kind of looks long, but please understand the way the exam works is it's like 3 big questions or something like that are divided into tiny, tiny parts. Like, I think it says at the beginning, every single part you get like is like worth 2 points. So it's divided into tiny, tiny little calculations, most of which we've done before. And your goal is to make comparisons ultimately in this exam. So it's all about doing forces on an inclined plane, one in different ways. So page 2 just gives you the setup. There's nothing to do. I mean, page 2, part 0 is a setup. It's just asking to draw the inclined plane and understand it and all that. And you should draw it. But then on page 3, so I'm just walking through, I'm just looking at now. I guess I should switch. We have 5 minutes. Okay, I'm just switching. Well, okay, so here I am at page 3. It's asking you to walk through to a system schema and then a pure free body diagram. You've done those a million times before. Please notice also, I'll tell you right now, the system schema is going to be the same, whichever coordinate system you're doing. The pure free body diagram is going to be the same for part 1 and for part 2. The system schema will ultimately have 3 lines in it. 1 for weight, and 2, like 1 that connects to planet Earth, 2 that connect to the inclined plane, 1 that ultimately stands for the normal force and the other that stands for friction. The free body diagram will therefore have 3 arrows in it. 1 will point straight down, the other 2 will go at sort of weird angles. Then in 3, where it says explicitly specify every Newton's third law action-reaction pair, it is trying to there will be 3 pairs because there's 3 forces, 3 arrows, there'll be 3 pairs. Like, and the action for each one of your pairs will be what you're seeing right there in the picture. I can even say the answer right now if it helps. I mean, for this part, it'll be like Earth pulls the mass down. That's like an action. Therefore, like semicolon or whatever, or colon, therefore, mass pulls Earth up. That's 1 pair. Okay, then you'll have another one like inclined plane pushes mass up and to the left, or however you draw your picture. And that's like the normal force. Therefore, block pushes plane down and to the right, something like that. Then now that's the normal force. Then friction is like plane pushes the block up and to the right. I mean, it all depends on how you draw your picture. So you got to be careful how you have to be consistent how you draw your picture. But so there's 1. So then friction is like plane pushes block up and to the right. Therefore, block pushes plane down and to the left. notice with every one of those pairs, if you use the word push in one side of the pair, you use the word push in the other, and vice versa. And if you say up in one side of the pair, then you say down in the other. And if you say I push you in one side of the pair, then you say you push me in the other. It's totally a pattern and a rhythm. But okay, so that's it. Then in part 4, it says use the coordinate axes and draw the component free body diagram. Be very careful there. Like I would even suggest doing a separate diagram where you just zoom in on the forces that you're breaking up. I will tell you right now, since I know we're like about to run out of time, and I'm just trying to do this to help not to freak anybody out. But like the whole issue, the whole difference between part 1 and part 2 is you're deciding what forces to break up and what forces not to break up. That all depends on which coordinate system you're in. So to be honest and to be straightforward, hopefully this will make sense to you when you're practicing. In part 1, you're going to break up the normal force and friction. You're not going to break up gravity. In part 2, you're not going to break up the normal force or friction. You are going to break up gravity. Maybe that makes sense to you right now. Maybe it'll make more sense to you in the next couple of days when you do this. Again, your final exam will look like remarkably similar to this, to just be hopefully shorter, but it will basically be this. So I'm flipping because I know we have 1 minute. So you're going to do the same thing in part 1 and part 2. There's going to be a lot of answers and diagrams that are the same, but when you get to the components, they become different. Then the F net equals MA calculations will be different. I'll tell you this too. I know we have 1 minute. If you're doing this right and following, your calculations will be different from part 1 to part 2. They will be different. Don't base your calculations from part 2 off of part 1. They're separate calculations. If you're doing this right, the calculations for part 1 will be longer and harder. They will. The calculations for part 2 will be easier. You'll land at the same place either way. You'll land at the same answer. Am I doing? Oh yeah, sorry. And sorry, friction. I'm sorry. There's no friction in this part. I was saying friction. Friction comes into the next part. But other than that, everything else I said the same. So then you go to part 3 when friction comes in. I'm sorry. So everything I just said is true, but just like then you go to part 3. Now you put friction in, and I'm telling you, the whole purpose of part 1 and 2 is to see that breaking up gravity is the easier thing to do for calculations. So now stick with that for part 3. You'll break up gravity. That's my advice. Stick with that coordinate system where you break up gravity. Everything else will not be broken up. You're dealing with friction now. The difference between up and down, everything will be the same in the 2 cases, except the difference between up and down is that friction will change direction. So in one place, it'll get a plus sign, and the other will get a minus sign. And then you'll plug in numbers and see the difference in the numbers. That's it. I mean, I know it's 1:30. Again, it's like a weird note to end on, but I want you to do as well as possible. If you watch other video, I'll be slower about going through the whole thing. You can text or email me at any time. It'll be posted in 2 days. I might post more hints or answers, but I think most of them you now have one way or the other. Please text or email with any questions. I very much hope to see you in 204 electronically or in person next semester. And there's something in the chat. Sorry, but I don't have to go. Okay. So thank you all very much. You've been a wonderful class. And if there's a huge alarm with one of your grades, last thing, sorry. If there's really a crisis, one of your grades, like if I really at the end actually think you're going to get a D or an F, and you haven't heard that warning by then, and all of a sudden it'd be a major surprise to you, then you'll get an incomplete instead. I should say this. I know you have to go now, but if anybody, heaven forbid, if you see incomplete on your report card, on your CUNY first, which I think you'd get warning if you were, but if you see that, it means that there's something wrong somewhere, either on my side or yours, and I want to have a chance to correct it so that you don't get a D or an F. Okay, so it means contact me. If you see an incomplete, it means contact me, and we'll figure out a way to work it out. I'm telling you that right now. Okay, so don't go into a panic. Just contact me if that happens. It means just that. Okay. But other than that, thank you guys thank you. Yes. Thank you guys very much. Sorry to keep you over. I'm rooting for you. Yes. Have an awesome holiday or winter break. Yes. All of you. Great. See you soon.
Bye, Professor. Have a good break. Thank you.
Thank you so much. Thank you. Have a great, yes. Thank you.
Professor. Hello.
Yeah, sorry, wait, let me stop the recording.